To continue the deep dive series on the Mark II, today we're going to be taking a look at the main blade. So those guys are these automatic blades that pop out of the top of the forearm. The old Mark I suit had a similar system, but that one wasn't automatic. This new one is actually being electrically activated to go in and out. We're taking some design elements from the Mark I and applying it here, but this guy's getting an upgrade. You know, we're going crazy, we're going big. The new Mark II is supposed to be an upgrade of the Mark I, so that's kind of where this is going. The inspiration for the system, you may be surprised, is actually Iron Man based. So in the Iron Man 3 movie, if you remember, one of the suits he uses has these blades that pop out at the top of the forearm. It's called the Silver Centurion suit, and that's where I got the main inspiration. You know, so still keeping with the Iron Man here, we're not drifting too far off the path, even though that's kind of what a lot of the suit does. But hey, also Pacific Rim, Gypsy Danger has these blades that pop out the arms, and they, you know, cut dragons in half and, you know, kaijus or whatever. But the main driving force behind this was, you know, just having a cool automatic blade that pops out, right? And you may be thinking, this sounds very similar to Assassin's Creed. Well, the difference there is that Assassin's Creed comes out the bottom, mine comes out the top. You can see it here moving. The blade is now electrically actuated. There is nothing that's forcing the blade out or in besides the electrical input that I'm giving it. And it's an automatic blade now. You know, we can go out, we can go in, we can lock at either position with new locks. And that's what we're going to talk about today, is how I got that to work. As I said, this system is inherited from the Mark I. And from the Mark I, there wasn't really any actuation behind it. You know, it was really just a blade that I had to pop out physically with gravity or with any sort of momentum. But the system itself had these locking mechanisms that were electrically activated. So the mechanism would lock in place either in the in or out position, and I could electrically undo those locks so I could move the blade in or out. That was the real main electrical system for the blade in the Mark I. Now we're taking that to the next level, having electrical locks while also having an electrically actuated blade. So with the Mark I, the way the locks work is that they were inspired by an out-the-front knife. The out-the-front knives have these switches that essentially unlock the blade so that it can fly forward with these springs inside, and then it basically resets the springs when the blade reaches the end point so that when you flip the switch again, it goes back inside. That idea is where the lock design came from for the Mark I. This lead screw would move this plate forward and backwards, and as the plate moved, it would move the locks out of the way or allow them to move freely so that the blade would either lock in the out or in position. So obviously there was some electrical control behind the blade, but that really only allowed me to pop it out or have to push it back in, which isn't as cool if you want an automatic blade, right? It's supposed to be Iron Man, it's supposed to be high tech, it's supposed to be advanced. We need something that's automatic, you know, response to motion, that kind of thing, right? Otherwise, you know, what are we doing here? Unfortunately, the locks in the Mark I, they were made out of 3D printed plastic, and any sort of impact that hit the blade would get transferred to the locks, and then the locks would probably snap. That could not transfer over to the Mark II, unfortunately. You know, it works great for the Mark I demos and all that, but in terms of robustness, in terms of withstanding impacts, plastic locks are not going to do the trick. A lot of the system for the Mark I has not really transferred over to the Mark II, hence why it's going to look very different from the Mark I in terms of design, mechanism, and all that. But the main thing is that the Mark II is now automatic. So the design process to get to where we are now took quite a bit of iteration. The design process for the side blades kind of had a more linear path to the current state that it is now. It wasn't so much redoing everything, it was just kind of improving and improving and improving the system until it got to where it is now. However, with the main blade, this guy, we had a little bit more of a battle with the designs that I wanted to go with. There was basically 3 big designs that I ended up choosing, and the first 2 failed, and the third one ended up working pretty good. The design process began originally thinking of a pneumatic system. So the Mark II arm originally had all the support for a bunch of pneumatic inputs on the forearm that would come from the bicep, and the bicep would take inputs from the chest piece where, you know, like a reservoir or like a compressor would be. So the first attempt essentially was a dual acting piston, and you can think about that as in having an air input on one end and an air input on another end that pushes the blade either out or in. I would have needed a much larger air compressor or a much larger air tank in order to store the higher pressure air that I would need to actuate the blade. And also keep in mind that even if I did find a way to do that and I maybe use like a paintball tank that's like 3,000 PSI, I would have to eventually run out. You know, I only get so many uses for a pneumatic system like that, and I also have all these tubes that would go from the forearm all the way around to the chest piece where the pneumatics would be stored. So unfortunately, a pneumatic system to control the main blade just was going to be too much extra hardware for such a small subsystem. Ideally, everything fits nicely into the forearm, so I kind of had too many space constraints to not be able to go with a pneumatic system. A couple of good things did come from that design phase though, and that was mainly the locking and the linear guiding system. So when designing the locking mechanism for the blade on the Mark II, the main inspiration there was one-way locks, right? So I'm trying to think of what's a system that can allow me to go in one direction but not the other. I thought more of like the springy things that are indoors that allow you to close the door all the way and then you can't pull the door back. And those have like this triangular profile that allow you to slide past one way and then you can't go back the other way. And I found these solenoids, which are essentially a magnetic coil that when they get turned on, they suck in a piston, and they have a similar triangular profile, the ones that I found. And those allow me to go one way with the blade, but then I can't go back but since they're solenoids, when I turn them on, the piston gets sucked in, the lock gets disengaged, and then I can move the blade backwards with the actuation system. And they actually made it all the way to design now, so that means I don't have to worry about the locking mechanism, at least for a while. Maybe it'll get improved in the future, who knows. For the current state of the suit, they're working as good as I need them to. Also, I mentioned the linear guiding system. In the Mark I suit, there was a channel that the blade would just slide through. If the blade rotated due to like poor tolerances or there was just some misalignment in the motion, it would actually get stuck as it tried to move because it would bind to the walls. So that behavior I try to mitigate in the new arm by actually adding a linear guide rail that the blade mounts to. So when the blade moves, it actually is kept on track with this linear system. And I'm using this very precise linear ball bearing rail that the blade screws onto so that it can slide linearly without having to worry about misalignment issues. It's low friction and helps a lot with that. Luckily, very early on, I was able to get the locking system and the linear guiding system out of the way. So that helped a lot with kind of prototyping on the next couple of designs for the actuation. That's really the main focus now, is just actuating the blade. You know, we have a way to keep it in place, we have a way to keep it aligned, but now we need a way to actually get it to move. So moving on from the pneumatic system, I started thinking about a little bit more futuristic, maybe more advanced technology to actually accelerate the blade. You know, I'm working in a very tight form factor. I can't really benefit too much from off-the-shelf components. That's why the whole suit, most of the suit is all custom design and all custom electronics, all that, because I really don't have much space to work with and I really need to tailor each system to fit within its designated profile. So thinking about linear actuation systems and some like higher tech ideas, I started thinking about, you know, magnetic acceleration. So thinking more about magnetic acceleration, a couple of ideas I came up with was using kind of a linear motor style thing. A linear motor essentially is a motor that's been unraveled where the stator and the rotor are no longer concentrically coupled. Essentially the stator rolls out into this flat plane that has all these magnets lined up on it because that's how it normally is rolled up. And now the rotor itself now becomes this linear slide that essentially floats on the stator and moves back and forth. However, that does require wires to be connected to the actual linear piece itself. The blade's gonna be taking impacts. It's gonna have to move pretty quickly forward and back. I'm moving a lot more than I did with the side blade, so any sort of active electrical connection thing is gonna be a lot harder to do. So trying out a linear motor system for the main blade just would have been too difficult to actually achieve properly and probably would have been too sensitive to actually any sort of impacts during the motion. Can't really go with that, but I still had the idea of like a magnetic acceleration in mind, and I started thinking more about the railgun systems that the Navy uses. So the Navy has these big railguns that have projectile inside that get accelerated with a magnetic field and they get launched out super fast. And I'm thinking, how can I incorporate that into my blade, you know? And the way this actually works is pretty cool. They basically have these two high power rails, positive and negative, and when you short them with the projectile gets accelerated through a thing called the Lorentz force, which essentially is a force generated by the magnetic field that's created when you short that circuit. And I thought that was pretty cool, because using a railgun to accelerate a blade would be pretty sick in my opinion. However, that also does require a lot of energy input. So the designs I started making for the blade, I had these two copper rails that the blade would slide on in order to short the actual rails, create the magnetic force, and then propel the blade. I also added a bunch of tiny magnets underneath the path of motion to actually enhance the magnetic field that was being generated to accelerate the blade forward and backwards. And you might be wondering how the direction of motion gets reversed for the blade. And that's actually done through just reversing the polarity. So if you remember the right-hand rule, that essentially dictates that if I reverse the electric current flowing through these rails, then I also reverse the magnetic field that gets generated, and then I can propel the blade backwards. In theory, of course, it sounds like it's going to work pretty good. However, that also comes back to another huge energy density problem that I'm having to deal with. So you can remember the pneumatic system, I would need a huge reservoir for air or an air compressor, but for the railgun, I also need a huge reservoir of electric charge. I need to create a huge voltage potential in order to create a huge magnetic field to actually accelerate the blade. And that also led me to another problem of energy storage. You can maybe think like a high power battery might work, but batteries have very low discharge current compared to like, you know, a capacitor that immediately discharges all of its charge as quickly as possible. And with capacitors, the amount of charge they hold isn't necessarily so much as a battery because they usually come a lot smaller and they just generally store less energy than a battery can. And with capacitors, if I were to buy some standard ones, they just wouldn't be able to do enough because they can't store as much charge as like a large battery could. You know, they're usually pretty small. And then if you think of a large capacitor bank, then I'm back to square one with a pneumatic system having a huge reservoir of energy either on the chest piece or somewhere on the bicep. That adds weight, that takes up space. We can't really do that again, right? So it's unfortunately going to be an unfeasible design. As cool as it would have been to have a railgun accelerate my blade, I just couldn't do it for now. So unfortunately with the railgun out of the way, you know, we can't keep going with it. It would have been equally as unfeasible to do as the pneumatic system. So now we have to kind of think of something that's a little bit better. Learn from our mistakes, learn from our design errors, and go from there. I started thinking more about my expertise as a mechanical engineer. That's my background, right? You know, I have electronics, I have software experience, but I went to school for mechanical engineering. Might as well try and use that a little bit more than trying to take some electrical inspiration. I started thinking about linear mechanisms. You may be thinking of like a lead screw. Lead screws just use a threaded rod that's attached to a motor, and then when that rod spins, it moves the nut that's coupled to the lead screw forward, and that's how you get your linear motion. Unfortunately, they're usually pretty slow, so I just wouldn't be able to get the speed that I wanted. And then if you think of something like maybe a rack and pinion, those are definitely a lot faster in terms of the motion. However, the actual design of the blade would then have to incorporate those teeth from the rack onto the blade in order to make it mesh with the gear, and then the whole design gets changed in the look and everything, and I just didn't want to have to deal with that either. No rack and pinion, no lead screw. Ball screws are also the thing. That's basically lead screw, but just more expensive at that point. I mean, it has better performance, but hey, I had to look around a bit, kind of come up with some ideas, and I saw my 3D printer, the old Creality CR10 V2, that has a linear system that moves the extruder back and forth, and that doesn't use a lead screw, doesn't use a ball screw, doesn't use a rack and pinion. It actually uses a belt carriage. So what that does is essentially mount something to the belt in a belt loop, so when the belt gets moved, whatever's attached to the belt also moves with the belt. So I'm thinking about how I can incorporate that into the blade design, and I started thinking about adding a motor and like a belt pulley, and the blade itself gets mechanically attached to the belt, so when the belt moves, the blade moves, and then we have ourselves a belt carriage system that accelerates the blade. And that's kind of where we ended up now. I designed these little metal connector blocks that the belt itself connects to. Those blocks thread into the blade, so the blade actually gets grounded to the belt, and that gives me the mechanical grounding that I need for the belt. And then the actual power input, I ended up using another DC motor, except it's a little bit more powerful than the one in the side blade, just so I get higher speed and higher torque. In the video at the beginning, I'm actually only using one motor, which means if I were to add my second motor and kind of finish it off, I would get twice the power. And that is exactly what we want for something that's supposed to be quick and responsive. I've tested it already, it broke before I recorded the video, if I'm being honest, so that's why I only did one. The linear rail is still in play, and the locks are still in play, and they incorporate very nicely into the system by allowing me to move the blade to each position, and then I can lock it at either position as well. And one more thing to go over, which I'd argue is equally as important as the motion, is the actual sensing, because you can't have controlled motion without a sensor to control your motion. So for the side blades, I used a Hall effect sensor to detect the presence of a magnet at either end of the blade's motion. So the Hall effect sensor wouldn't have worked as easily, because then I would have to put a magnet on the blade and would have to deal with all the motion back and forth. I would need one at either end, and that's a whole thing, right? And we can't put the sensor on the blade because then we need an active electrical connection throughout the entire motion. Also not going to work, going to be too hard to do. I started thinking about using the impact of the blade at either position as a way to capture the motion. Originally, I had these dampers in place at either end of the blade's motion to protect the frame of the suit from breaking, since the impact could be pretty harsh sometimes. And the idea was that I would use those damping features as also sensing features. So I started thinking about buttons, which are springy things themselves, but they also provide a signal when they're compressed. And that actually gives me a signal that tells the motors to stop the blade from moving. There wasn't much iteration there, and those are actually what we're using today. They're on these custom breakout boards, nothing too crazy, just to physically mount them and actually get an electrical connection easily to them. There's also some custom motor drivers and a custom microcontroller that went into this guy, but it's the same ones that I was using for the side blades, so not much new designs there. But hey, that's where the main blade is. That's kind of where we are now. The blades and all that, it's like the melee, it's the fun stuff. It's the more like vigilante, kind of street level inspired technology. But the rockets and the flamethrowers and all the more combustible, the more volatile things, that's Iron Man right there. You know what I'm saying? So look out for that.